Thank you, and thanks everyone for being here. What we're going to present today is work that the University of Idaho has been doing here in the Coeur d'Alene area as part of the National Science Foundation project managing Idaho's landscapes for ecosystem services, which looks at how climate change and urban growth have an impact on ecosystem services around our mid-sized cities. So the University of Idaho is specifically working in the Coeur d'Alene area. And the way we do this work is we engage the stakeholders as part of the research process, which is why this becomes incredibly relevant for the topics of today's conferences. Our study area is specifically just north of where we are right now. We are here, and this is Fernand Lake. It's a small tributary lake to Lake Coeur d'Alene, formed by glacial flood deposit damming many 10,000 years ago or so. Has a small watershed and is right next to the city. It is the state's most heavily fished recreational fishery by acre. As you can see why. You can get on a bicycle and you can be there in 2 seconds, and lots of kids do, lots of other people do too. But it is also challenged, as you can almost see in this picture, from blue-green algae blooms. And the stakeholders there, not only the landowners in the region, but also the IDEQ and others came to us and said, we don't understand enough what's happening here, can you help us? And we initiated our project in the study area. The algae blooms are intense. It's still ongoing this year. It's started in approximately June and is still going on. It's a cyanobacteria bloom, so it's toxic. It's not just doesn't look nice, it's actually toxic, so everyone has to stay out of the lake and keep their dogs, their kids, limit fish consumption, all the things that go with that. And it has a direct effect on the community that lives there. As part of our process with the MILES program, we are trying to characterize the social dynamics of the system as well as the ecological dynamics of the system, because as we know as climate scientists and others, you can have as much hard data as you want on what's happening in the ecology and the atmosphere and everything else, but unless you actually know what people know about it and how they are going to receive that information, you don't have a way of getting it to them. So we started by talking with the community through surveys, through interviews, through focus groups as to what is their relationship to the lake, what is their knowledge of this issue, where do they think it's coming from, et cetera. And one of the many questions, how at risk is your community? Most people thought it was highly at risk from the algae blooms. But then we start digging into the data a little deeper, because we geocoded all of our responses and we were able to determine that there's a gradient of response depending on where people live within the community, if they're up the valley in the watershed, if they're in the more urban area, and be able to fine-tune the information that they need to hear or the information they need to know based on real geographic considerations. Because it's real easy for any of us to come up with a program that says that here's the information you need to know and then just distribute it to that community, but unless it is specific to what their interest in the issue is, it will just slide right off of them. So one of the things we talked about with them was timber management, because the upper portion of the watershed is primarily National Forest Service with some major private timber landowners in there. And we asked them what their goals for timber management were. Forest Service is pretty easy to understand. They have forest plans, but it's difficult to gauge individual behavior until you actually ask them. This is what they thought. None of them were into it for the economics of forestry, but they were going to continue active logging management necessary to preserve the health of their stand. Had they seen impacts of climate? Well, they really couldn't tell, but if they were going to see it, they would probably actively manage their stand to do something about it. But it wasn't really on their radar. They didn't have that information at this time as to how they might think about management, which then starts to drive the characterization process that we do through the research scientists on the other portions of our team, one of the things we did was typify and characterize the sources of phosphorus, which are the drivers of those blue-green algae blooms. Because remember, all of what we're going to present to you here is all focused on what does it take to make a blue-green algae bloom occur within this watershed, within this lake, and what are the actions that are going to happen in the watershed that are going to make that less likely or more likely. So now we know from doing this that we have a lot of phosphorus that's coming bound to sediment down the creek from the upper portions of the watershed. And with that, I'm going to turn it over to Aaron Brooks. We'll talk about how we took that information and started to work with it on the landscape.
Okay, so just a quick taste of what we're doing with it. Talking mainly about biophysical modeling of capturing where is it coming from. So where's the sediment coming from, and then the climate change part of this. If it's a sediment issue and timber management is a part of it, what happens to wildfires come in? At what point does this become an issue? So just give you a quick snapshot of what we're modeling here. It's as a typical watershed where you don't have a stream gauge station located on it. For modeling, I guess that's good because you don't have much validation, but we do want to have some confidence that we have a model that's working right. So Lake Hayden watershed had some historic stream flow records to it, so we were applying a model to this watershed. We're going to show you a little bit of some of the confidence we have in the model. It is a spatially distributed model. We use is the Water Erosion Prediction Project model, and we're using that in conjunction with a fire model, FLAM map, to actually evaluate fire risk and the impacts of sediment with the combined model. So we have two different watersheds we're looking at. We're using the Hayden Lake as kind of to calibrate, validate the model, and then we're applying that model to Fernand Lake. Fires are, we did a historic analysis on fires and when do they happen, the frequency of the fires, with the information that we can get on current timber fuel availability. We can run the FLAM map model and actually get a fire severity. So this is currently what it looks like in terms of high burn severity if we had a wildfire going through. This is kind of fire severity. And with the model that we have, with the wet model combined with this fire severity map, then we can predict sediment loads. So here's sediment load prediction. This is by hill slope. The model can actually also do it by grids if we want. And you kind of see the spatial variability. This is where sediment is likely to come through with a wildfire, and we can run with wildfire and without. Interestingly, some of the spatial patterns you see are actually align well with some of the geological dating we're actually doing on this project. It's not a part of this talk, but at least more confidence in the model. Hayden Lake, how does it look? Snow depth, the predictions actually look pretty good. Stream flow as well. We're getting a pretty good match with the model on that paired watershed. In terms of fire, so how's climate change going to affect the fire frequency into the future? What we're doing now is using the model as an ability to predict fuel loads or the moisture contents and the risk of wildfire. So how many days per year are actually in a high risk of fire, and are those number of days going to increase in the future or not? So these red dots are showing where actual fires in the last since 1990 when have taken place at. And we did a model run for predicting soil, using soil moisture as a surrogate for fuel moisture, and say when did these fires come, how dry was the soil, and we say maybe that's an indicator of how dry the watershed was. And you can see once it gets below about 10 millimeters, and this is predicting the top soil layer of water in the soil, then we're calling these high risk time periods. So we have moisture content, so we can use in this model to say, well, if you're between 10 and 20, there's a moderate risk and a low risk once we have a moisture content above 20. So we can use that as a way to assess what's the risk of wildfire into the future. And then we can run the model for different scenarios into the future and say, here's the number of days of fire risk days, so less than 10 millimeters of water in the soil. And if we can do this with here's an RCP 6.0 scenario. And with this, then we can say, based on is a cumulative distribution with times from 2026, 2046, 2066, and 2086, the number of high-risk fire days. And we can see from the current time periods to now, we're going from about 40 days per year to 50 days per year in this climate scenario. So the RCP6 which is a little bit more moderate. We're going to do something about greenhouse gases. If we go up to an 8.5, which seems at this point a more realistic scenario, now we're up to about a 15-day increase in the, oh, I'm going the wrong way, sorry. About a 15-day increase in the number of high-risk fire days. So we can see, obviously, the fire risk is going up. So just a snapshot of the biophysics modeling.
So Roger Liu's going to get up next and talk to us about it. But now what we do is obviously what Aaron just talked to you about. We can present that to stakeholders. They won't have a foggy idea what we're talking about. So how do we then take that and communicate it to them?
Right, so like I was going to say, you know, those slides work great if you have Aaron, but you can't always like pack Aaron in your suitcase or like deliver him through the internet. So what we're looking at are immersive virtual landscapes. And since I'm one of John's replacements, I should say something that John would usually say. And so he likes to ask people, how do humans learn? And we learn by playing. And that's kind of the idea with these immersive landscapes. You can get in them, you can turn dials and knobs and interact with the environment and see what is going on. And here, this is really kind of illustrating the fact that we're using Unity 3D. It's a game engine. If you're not familiar with video games nowadays, you should find a 16-year-old and then steal their PlayStation 4 away from them for a couple hours just so you can see what these things look like nowadays. But you know, they're highly immersive, and the ability to bring that into research or for other applications is getting easier and easier. And that's a lot of what we're looking at, how we can take tools that aren't really designed to ingest geospatial data and do that in an effective way by using Python to develop you know, visual assets which can then be ingested into Unity. And for time, I'll just kind of move forward now, I think. So we have a video demonstration of what this immersive environment would look like. And the real thing, you could walk around, you can fly like Superman, you can do all sorts of things. But for time-wise, we'll just play the video. So we have virtual Fernan here. The terrain that you see is generated from LiDAR data, and then it has ortho imagery on top of that. And then here we see Fernan Lake. Some of our colleagues actually went out and collected bath imagery data of the lake, which we've incorporated into this model. You'll see all those little dots there. That's them actually going back and forth in their boat to collect those points. We also recreated the docks to provide a frame of reference for the stakeholders, so they can say, okay, yeah, that's my dock. So if the water's at that level, like, I have an idea what that would look like. Eventually, those will show historic stream flow data that we collected throughout the course of a year. And that'll allow you know, stakeholders to review what happened to their watershed and correlate that to lake levels and to the phosphorus loading and algae that's in the lake. So eventually, we'll build in a mass balance model that will allow them to go in and turn the dials to see what's going on. One of the neat things about the game engine is we can simulate weather patterns. So you could, you know, show them, okay, well, you know, here's a rain on snow event, or here's, you know, precipitation or whatever else. And then this is kind of showing how the sky is changing. And then lastly, we've taken some of the web data that was provided by Anurag and Aaron. We can overlay it on the hillside, and now we have you know, sort of like a first-person perspective, and it's easier to correlate. Okay, yeah, that region up there, that's by, you know, so-and-so's house, or that, you know, it makes it easier to sort of like locate what is actually where in the landscape. And this is showing you know, the prescribed fire versus no prescribed fire. All right.
So, you know, the challenge has always been taking that science data that we are familiar with and translating in a way that can be used by the people in the watershed. This visualization is now on our website, idahoecosystems.org. People can go in there, they can change the sliders. Pretty soon we'll get it to the point where they can say that, well, okay, I'm going to go log, or I'm going to burn off 200 acres up here, and then see how that translates in terms of turning the lake green. Because remember, this is all about what does it take to create an algae bloom in the lake. We could choose a different threat, build it in for a different type of output, but you know, the idea that we want to take what are complex data sets, translate them into ways that you don't have to have a PhD to actually understand, and be able to see what that means when it gets to your landscape. And this is the loop we use to do that in the project, because we keep the stakeholders in it all the way around. We ask them the question, we present them the information, and when that always raises more questions, we come back and we do it again.
Thank you. We have time for questions.
So I guess I'm really interested in, so you have a pretty iterative feedback process with your stakeholders. Where was the initial impulse for the visualization scenarios in the first place? Was that something that stakeholders requested or were interested in, or was that an idea that you floated, went with because of that, like evidence that that's one of the most effective communication tools? Or I'm wondering about the inception.
The inception actually started with the capabilities and capacities we have at the university that were built into our proposal to NSF for this project, where we said that, you know, this whole idea of communicating science is complicated, and we want to try applying our virtualization technologies to it. So then when the local stakeholders came and said, here's our issue, we said, okay, this is what we'd like to try to deliver to you. And they said, great, let's go for it.
I wonder if you can explain a little bit more about the fire model. What's the mechanics behind that, and is it
So the fire severity modeling, or the impacts of the fire severity on the sediment?
I mean, how the fire model really works and how that works with your hydro model.
That's a lecture and a half there, but more or less, it's so FlemMap is a model that you can take current canopy load, so it'll canopy density, canopy height, and it then will take weather data for a certain time period and get a fuel moisture amount. And from that, you run a fire model with a wind distribution and say, okay, this is a certain fire severity from that. And we take that fire severity map, and then with the model, the hydrologic model, then we're saying, okay, now we have a certain surface cover condition is lost. We've lost our residue cover. The soils may be hydrophobic, depending on the severity of the fire, and then it runs it through a daily erosion model, the wet model, to run through and actually predict the sediment. That's the short answer. I could follow up a lot more detail after that.
So the application of that, though, is we've produced maps that show that if the landowners go in and do certain types of prescriptive management on these certain hill slopes that have high erosive capacity, they can significantly decrease not only their fire risk, but also the amount of sediment that's going to impact the lake.
One more question. Yeah.
Yeah, I didn't quite get your answer to the people around Grand Lake or stakeholders didn't know about climate change, or what was it? Said something like, I don't know about climate change.
So when we did our initial social characterization, we asked questions about you know, what would drive their future behaviors, and climate change was certainly evident in the answers as something that they were aware of and knew that was going to be affecting them, but they did not have any concrete sense of what it was doing to them currently or what it might be doing in the future.
So there's a gap of understanding.
Right. They were aware of it, they understood it was an issue, but how to do anything about it personally, they didn't have a good grasp.
Okay, thank you, Trifecta.